Welcome back to the final part of our four-part series on HVAC design requirements for New York City School Construction Authority projects. In this session, we'll cover refrigeration system documentation, miscellaneous HVAC drawing standards, split heat pumps and VRF systems, and air-to-water heat pump requirements. This will complete our walkthrough of Section 6.2, giving you a full picture of what SCA expects from HVAC design. When we talk about ducts that require dedicated shafts, the focus is on safety and compliance with NYC mechanical code. First, certain ducts cannot share space with other services. This includes ducts for grease and smoke exhaust from kitchens, ducts for flammable or corrosive vapors, ducts moving dust or stock, and also refuse or linen chutes. Piping is also excluded, except for non-combustible water lines or other safe, non-toxic materials. Because of this, some ducts must always be run in their own dedicated shafts. These include kitchen exhausts, gas meter room exhausts, science lab fume hoods, sub-slab soil exhausts, and oil tank ventilation ducts. For kitchen grease ducts specifically, the rules are strict. Any grease duct that passes through a ceiling, wall, or concealed space must be enclosed from the penetration point to its discharge outdoors. Inline fans that are not outdoors also need to be enclosed in fire-rated rooms with proper ventilation and cleaning access. Importantly, these enclosures can only contain the grease duct, no other pipes or wires. And fire dampers or smoke dampers cannot be installed inside grease ducts. As for fire safety, duct enclosures must match the fire rating of the assembly they penetrate, but never less than 1 hour. The only exception is when a grease duct penetrates a non-rated roof or ceiling. From a design perspective, the preferred option is to use a dedicated shaft enclosure and show it clearly on the drawings. This approach avoids workmanship issues with insulation wraps or prefabricated enclosures. If non-shaft options are used instead, they must be explicitly indicated in the design and properly edited in the specs. This section lays out how refrigeration systems must be designed and documented for school projects. First, ASHRAE 15 introduces the concept of EDVC, the effective dispersal volume charge. It's essentially the maximum amount of refrigerant allowed in a single circuit so that, even if all of it leaks into a space, it won't create unsafe conditions. For A1 refrigerants, EDVC is based on concentration limits, while for A2L refrigerants it's based on lower flammability limits. Because A1 refrigerants are being phased out, all systems should be designed with A2Ls. Construction documents must clearly show critical details: equipment location and size, refrigerant type and quantity, ventilation methods, detector and emergency switch locations, pressure relief piping, and safety group classification. Designers also need to include refrigerant concentration limit calculations and piping routes. Refrigerant piping rules are strict. Piping below 7 feet 3 inches must be concealed or protected. It cannot run through shafts, stairways, elevators, or exits. In corridors and lobbies, only factory-assembled, unit systems are allowed. Split systems or VRF piping are prohibited. Both A1 and A2L systems must meet EDVC charge limits, and if exceeded, designers must either break the system into smaller circuits or add continuous ventilation. For A2L piping, continuous ventilation is the preferred option. Designers must size ventilation airflow properly using ASHRAE formulas. In many cases, leak detectors and interlocks with the fire alarm system are required. Shafts carrying refrigerant piping must be ventilated, either naturally or mechanically, with natural ventilation being preferred. If refrigerant charges exceed safe levels, mitigation strategies are required. Using multiple circuits, adding ventilation, installing solenoid valves with leak detectors, or enclosing piping in gas-tight shafts. Systems must also shut down compressors and alert the BMS if leaks are detected or fans fail. Finally, designers must consider machinery rooms for larger systems, proper exhaust, transfer inlet placement, outdoor unit ventilation, and continuous outdoor air intake when refrigerant exceeds EDVC values. The bottom line: refrigeration system design must balance refrigerant charge, ventilation, piping safety, and emergency response features, while ensuring clear documentation for approval and construction. This section covers the miscellaneous but critical details that must appear on HVAC drawings for school projects. Designers need to show more than just equipment layouts. For example, strainers must be indicated for coils, pumps, and traps. Insulation requirements must be properly noted depending on temperature differences and condensation risks. And all pipe diameters, duct sizes, and operating temperatures must be clearly documented. Load calculations, room temperature requirements, and sensible versus latent cooling capacities must also appear on the drawings. Designers should show how loads were calculated, ensuring compliance with ASHRAE and NYC codes. There are also important coordination items: location of condensing units, condensate piping, fuel oil pipe shafts, shaft sizing, and avoiding ductwork over partitions. Dampers, isolation valves, condensate lines, and combustion air damper visibility are all details that must be called out. Some very specific requirements exist for older schools and retrofit projects, such as aluminum ductwork for wet areas, replacement of rooftop dunnage, insulation standards for combustion air ducts, and proper fire, smoke damper access. Finally, drawings must account for structural realities: cinder concrete slabs, proper supports, shaft extensions, fire stopping, and adequate shaft spacing for duct supports. Designers must also coordinate flashing details with architects, plan for future re-roofing, and ensure shut-off valves for steam radiator traps and risers are shown. In short, this section is about capturing all the small but essential details that prevent problems in construction, code compliance, and future maintenance. This section explains how split heat pumps, vertical unit ventilators, and VRF systems can be applied in school projects. First, let's look at auxiliary supplemental heating. This is extra electric heating that kicks in when the outdoor heat pump alone can't meet the load during very cold weather. If the heating load is modest, up to 450 BTUH per linear foot, it can be handled with electric resistance coils inside the units or with baseboard heating, depending on the type of indoor unit. For larger loads above 450 BTUH per linear foot, electric baseboard heaters must be installed in the space. Then we have backup redundancy heating. This is protection for when the outdoor unit fails entirely, like from a refrigerant leak or compressor issue. In that case, electric heating must step in to keep the space warm, ensuring at least 65 degrees Fahrenheit tempered ventilation air. The acceptable system types for occupied spaces are 1-to-1 split heat pumps, VRF systems with multiple indoor units tied to one outdoor unit, and packaged vertical unit ventilator heat pumps that use outdoor air through a wall louver. DOAS units may be roof-mounted or located inside a mechanical room, depending on space, roof use, and aesthetics. If ceiling heights don't allow a central DOAS, a local ERV can be considered, but designers must ensure the terminal units provide enough latent cooling since ERVs don't handle moisture removal. Other requirements include: refrigerant charge must not exceed ASHRAE 15 EDVC limits, all refrigerant joints must be brazed, no press fittings allowed, condensate pumps must be provided, and VRF installations must be performed by OEM certified installers. For smaller buildings under 20,000 square feet, ceiling-mounted or closet-mounted ducted VRF units may be used, but larger schools must use closet-mounted units to avoid excessive ladder-based maintenance. Heating capacity must be calculated without relying on passive heat sources like lighting or occupants. Units must be capable of maintaining 72 degrees Fahrenheit during winter design conditions and reheating setback spaces from 55 degrees Fahrenheit. Because heat pump performance drops at low temperatures, supplemental electric heat is always required at 13 degrees Fahrenheit design conditions. Finally, designers must also account for humidity control. Since split and VRF terminal units have limited dehumidification, the DOAS units should be designed to handle latent loads, keeping spaces at below 50% RH at 78 degrees Fahrenheit. In special cases, like pre-K classrooms, playrooms, libraries, or clinics, these systems may be used more widely, provided they meet SCA requirements and project-specific constraints. This section explains when and how air-to-water heat pump chiller heaters can be used in school projects. The preferred option is rooftop packaged DX heat pumps, since they come factory assembled with refrigerant lines and full OEM controls. However, in some cases, air-to-water heat pump chiller heaters may be justified, for example, during building electrification retrofits or site-specific conditions. Designers must document justification in the electrification field report and submit equipment selections through the carbon reduction matrix for review. Air-to-water systems are more complex than packaged DX units. They require coordination between the chiller, heater manufacturer and the temperature controls contractor, especially for pumps and bypass valves. No equipment submittal should be approved before control submittals demonstrate this coordination. From a heating perspective, two types of backup are required. Auxiliary supplemental heating for times when the heat pumps are running but can't fully meet the load. Emergency backup redundancy heating for when the heat pump plant fails entirely. Backup heating must equal 75% of the plant's heating capacity. The preferred solution is 2 electric boilers at 37.5% each. The 3 boilers at 25% each may be used where installation conditions make it necessary. Chiller heaters must be sized based on the larger of the heating or cooling load, not just cooling, to minimize boiler use. They operate in a primary-secondary loop arrangement, with glycol in the primary loop and non-glycol water in the secondary loop. Secondary loop boilers raise hot water to about 135 degrees Fahrenheit at 13 degrees Fahrenheit outdoor conditions for fin tube radiation, or about 120 degrees Fahrenheit for fan coil units. Air handlers and vertical unit ventilators in the primary loop still need their own resistance heating for backup since the secondary boilers don't cover them. Manufacturers can provide at least 125 degrees Fahrenheit water at 13 degrees Fahrenheit outdoor temperature, and that is the design baseline. If needed, a thermal storage tank may be added to maintain minimum water volume. Coil selection must also follow ASHRAE 90.1 efficiency rules, with certain exceptions for high-pressure drop or special systems. Finally, all units must comply with all listing standards. Starting January 2024, only A2L refrigerants like R32 or R454B are permitted for new equipment in New York State, although older A1 refrigerant units may still be used if manufactured before the cutoff date. In short, while rooftop DX heat pumps are the standard, air-to-water chiller heaters can be a viable option if carefully justified, properly sized, and coordinated with controls and backup systems. That concludes Part 4 and the full walkthrough of HVAC design requirements in Section 6.2 for SCA projects. We've now covered everything from acoustics and seismic criteria to refrigeration safety and advanced heat pump systems. If you haven't already, be sure to check out Parts 1 through 3 of this series for the full picture. Thank you for following along, and don't forget to like, subscribe, and share this series with other professionals who work on school HVAC design in New York City.